welcome to module 2 on Phasor estimation, and we will continue with the least square technique. So, in this lecture our focus will be on how we can formulate the least square estimation technique and how this can be applied to Phasor estimation perspective, and in particular the fundamental component which I like to estimate for the relay. So, with this target we will go with this. So, let us first understand what is least square estimation technique before applying to the for the relay applications. We consider a set of measurements that satisfies A plus B t equals to m, where t stands for the time index and m for the measurements. Now, A and B are the system parameters which happen to be not known to us, and these unknowns are to be estimated in this process. Such least square estimation technique you might have come across in the curve fitting techniques or as a tool in signal processing. We are addressing the same thing here. Now, what happens here in this case, we have a set of measurements and the corresponding at different time in this time you can say that perspective. Now, let us you can say that we say that we have n number of measurements for this purpose. So, therefore, that m 0 through you can say that m n minus 1, and the corresponding time where we took these measurements are the t 0 to you can say that to t n minus 1. So, for this you can say that individual you can say that measurement and the associated time we can write the for the you can say that for corresponding system you can say that A plus B t 0 equals to m 0, and at t 1 time index A plus B t 1 equals to m 1, and like that. So, we will have you can say that a set of n equations for this. So, in this case you can say that these corresponding measurements are associated the corresponding time. Note that the time index you can say that the time you can say that t 0 through t n minus 1 are also known to us, and so also you can say that the corresponding measurements are also known to us, through which we like to consider that find the corresponding A and B values for the system as system parameters. These you can say that time you can say that intervals between two you can say that consecutive measurement points, generally they remain to be fixed, and that is what we will see can say that in our relay applications. Now, considering that the A hat and the B hat as our estimated values. So, in the same equation we can fit you can say that for the system equation like this A hat plus B hat t naught minus m naught equals to an error which will be there because the estimated one will not exactly match with the A and B. So, that will be epsilon 1, and like that you can say that for the other measurements also you can say that we write down epsilon 2, epsilon 3 like this. So, if you have the set of measurements here m naught through n minus 1 or m 1 through m n, t naught through t n minus 1 or t 1 through t n, what the set of measurements we here you can say that here m naught through m n minus 1. So, you have n measurements. So, E 1 through E n minus 1. So, this will be you can say that we have this will be E naught through E n minus 1. So, we can have you can say that n errors. So, these E naught through E n 1 are the errors, or otherwise we call residues also, and m naught through m n minus 1 are the measurements. So, and we are the estimated value A and B we like to get you can say that that you can say that are the obtained estimated values for this particular system. Then we can write this corresponding equation in matrix form like this, that 1 1 1 in the this, and then t naught you can say that in the second column t naught through t n minus 1, and then you can A hat, B hat, the estimated value minus m naught through m n minus 1, and that equals to E naught epsilon naught through epsilon n minus 1. So, you see that these you can say that are nothing but we can designate them as matrices, and these matrices are A matrix here, X matrix here, M here, and the epsilon here matrix. So, the X here is our unknown, that is A and B are to be obtained, and M are our measurements, m naught through m n minus 1, and then you can say that we can fit the corresponding equation also in the other way. We can write down that the epsilon, the error you can say that matrix that becomes equals to A into X minus m, where A you can say that is the matrix which constitutes the elements 1s and the t's. These t's are the under the observation. So, that is why these are known to us, the time index you can say that are considered to be known to us. So, if you say you can say that for these n sets of measurements n cross 1. So, we have n cross 1 for the epsilon, and for A you can say that if you see here n cross 2, and the x you can say that 2 cross 1. So, we have you can say that the matrix matching you can say that happens to be there in that way. Now, we will try to formulate the technique you can say the least square estimation technique. So, the epsilon, the error matrix, that becomes equals to A x minus m, that we have already seen earlier slide. If you multiply this epsilon with this its transpose epsilon t into epsilon, that becomes equals to this is epsilon, the transpose and this. So, multiplication of this will consider will provide us like this. So, this is A x minus m transpose, that becomes equals to this whole A x transpose minus m transpose, and then into A x minus m. Now, if you multiply these two, you can say that parts, then that becomes equals to A x transpose into A x, and then the m transpose into m. So, this will be plus minus this A x transpose into m, and the minus m transpose into A x. So, these are considered two quantities here and two quantities here gives us these 4 quantities. Now, we will see in this you can say that these terms, if you see you can say that here the m is n cross 1. So, therefore, m transpose will be 1 cross n, and the A is n cross 2, we have already seen earlier slide also, and the x is you can say that 2 cross 1, A and B are the two unknowns. So, therefore, the A x gives us you can say that n cross 1, n cross 2 into 2 cross 1, n cross 1, and the m transpose is nothing but 1 cross n. So, therefore, m transpose A x, m transpose A x, this term that becomes 1 cross 1. So, that leads to you can say that this for 1 cross 1 matrix, that is m transpose A x, we can write also, because transpose you can say that of the one element matrix, that becomes itself the element and the matrix. So, therefore, we can write the m transpose A x into transpose of that one. So, this m transpose A x that becomes equals to m transpose A x and transpose of the whole matrix, because this is 1 cross 1 matrix. So, therefore, as per the property of the considered transposition, we can write also A x transpose m, and that becomes equals to x transpose A transpose m, because of this matrix property transposition of this one. So, this leads to that we can write in place of this you can say that part, we can write out x transpose A transpose m, and therefore, if you see the consider this equation, we can represent this equation epsilon t into epsilon, that equals to x transpose A t, the first term, into A x plus s m transpose m minus 2 in consider x transpose A transpose m. So, therefore, we say that you can say that these two terms you can say that they become equal, and they gives us you can say that this part. Now, leading to that, borrowing that equation from the earlier slide, we will differentiate this you can say that equation with respect to x, and the reason we can say this part is nothing but epsilon square summation of you can say that all elements epsilon naught square, epsilon 1 square plus epsilon 2 square and so on till you can say that the epsilon n minus 1 square and n number of elements in that part. So, this summation, and then you can say that to that one summation we try to consider that differentiate, and that is you can say with respect to x, x is our you can say that the unknown vector. So, if you differentiate to consider this with respect to unknown vector, then we are getting you can say that and making this corresponding differentiation of this part to be 0. So, therefore, least square. So, that sense we can say that we get this part, there are 2 x here. So, we get 280 A x minus 2 A transpose m from this part, and this part does not have any x. So, that becomes 0 in this differentiation process. So, this and this gives us these two terms, that becomes 0 with you can say that least or minimum, you can say minimization problem. So, therefore, from these two you can say that, but from this relation we get this A transpose A x equals to A transpose m, and that leads us to can say that x, the unknown vector, becomes equals to A transpose A inverse into A transpose into m. Agree? This is the solution to obtain the corresponding unknown parameters of the system A and B as we have defined for the system A plus B t equals to m, where m is the set of measurement, A is that we know this 1 and t's it contains, and then A and B are the unknowns. So, in this case A matrix is also known to us, and so also the measurement you can say that matrix is also known to us. So, therefore, the right hand side things are available to us. So, we can find out this x vector that contains A and B, the unknown parameters of the system. So, this you can say that A transpose A inverse A and into A transpose is called the pseudo inverse or left pseudo inverse in the literature. So, once we have this inverse part and then multiply the measurement set, then we can find the corresponding x perspective. Now, see here that if this you can say that matrix A becomes a square matrix, then the whole you can say that term becomes an simple A inverse. Agree? So, that you can say that the simplicity, but what we say that we will see that the number of measurements becomes within our positions. So, we can have n number of sufficient measurements to find the corresponding correct value of x. So, in most of the cases we will find that this A matrix becomes no more you can say that square. So, that becomes rectangular, where the pseudo inverse matrix having these 3 terms you can say that are being considered being used for the to obtain the corresponding unknown you can say that x parameter in the x you can say that having these 2 parameters A and B. Now, let us you can say that how this corresponding least square estimation process that we define x equals to pseudo inverse of A into m, that how we can apply you can say that for this power system application, particularly relaying perspective we will see now. Let us the signal V n, that is nth sample, becomes equals to V sin omega t n plus theta. This kind of signal we have already used in the DFT application also, where V n is the sample at t n instant and V theta are to be found out. These are the 2 unknowns V and theta, which will reveal us you can say that the corresponding phasors. Agree? V is the peak value. So, V divided by root 2 is the RMS, and theta is the corresponding angle of this you can say that phasor at you can say that at the reference instant t naught or so. Now, then you can say that let us you can say that at one instant t equals to t naught, that is our starting time for the measurement. So, that V naught becomes V sin omega t naught plus theta. So, if we expand this we can say that relation. So, we have you can say that 2 terms V sin omega t naught plus cos theta plus V sin theta cos omega t naught. So, therefore, you can say that we can write down V cos theta sin omega t naught, V sin theta cos omega t naught. T naught is the time that is our in the under our control on measurements. So, we know it, and the V and sin theta are unknown. So, this part is not known, this part is not known. So, that is our you can say that 2 unknowns. Agree? So, these 2 unknowns you can say that V cos theta and V sin theta. So, we define this V cos theta and V sin theta in terms of x 1 and x 2, the 2 unknowns, and the corresponding other parts of this you can say that 2 terms sin omega t naught and the cos omega t naught, we define them at a 01 and a 02, 2 coefficients of these unknowns. So, this becomes equals to you can say that a 01 x 1 plus a 02 x 2, and that is what naught for the corresponding measurement V naught, where V naught is our measurement the voltage sample at t naught. So, we defined a 01 equals to sin omega t naught and a 02 equals to cos omega t naught, and x 1 equals to V cos theta, x 2 equals to V sin theta, x 1 and x 2 are you can say that our unknowns, and A's are nothing but coefficients. We relate to consider the capital A in the least square formulation. Now, similarly, at next instant after the time delta t equals to t 1, we got another sample V 1, and that you can represent in terms of V sin omega t 1 plus theta, and then that becomes, if we expand the like above, we can say that this becomes 2 terms, where the V cos theta term again comes, and this will be considered sin omega t 1, sin omega t 1, and this you consider v sin theta, you consider cos omega t 1. So, therefore, you can say that this becomes equals to a 1 1 x 1 plus a 1 2 x 2, where x 1 you can say that again same b cos theta and b sin x 2 becomes b sin theta, and the corresponding a 1 1 will be sin omega t 1 and a 2 2 will be considered a 1 2 will be considered cos omega t 2. So, with a 1 1 equals to sin omega t 1 and a 1 2 equals to cos omega t 2 and x 1 equals to b cos theta and x 2 b sin theta, we can get the corresponding relative you can say to the next second sample. Similarly, you can say that we can have n number of samples from v naught to can say that v n minus 1 for the considered measurements, and we can relate the corresponding equations from a naught 1 x 1 plus a naught 2 x 2, and like this you can say that to this for this v n 1 v n minus 1 you can say that a n minus 1 1 x 1 plus a n minus 2 you can say 2 2 x 2 like this, agree. So, this is the set of you can say that set of equations for a set of measurements we can write as we formulated for this least square sense also. Now, here you can say that for the particular you can say that v sin the sinusoidal signal of the voltage, we can write you can say see the corresponding a naught 1 becomes equal to sin omega naught, a naught 2 equals to cos omega t naught, and a 1 1 equals to sin omega t 1 and a 1 2 equals to cos omega t 1, and like that you can say that these coefficients you can say that well for the unknowns x 1 and x 2 are like this, where we will now formulate you can say that the matrix A we designate you can say in terms of a naught 1, a naught 2, a 1 1, a 1 2 and a 1 minus 1 1, a 1 minus 2 2. These are the considered set of you can say that terms A. Note that these A's are nothing but in terms of the time index and the corresponding frequency omega the fundamental frequency. So, therefore, you can say that in the t naught t 1 and t index in the time index being known to us. So, A matrix is assumed to be known to us. X is the unknown x 1 and x 2, where x 1 and x 2 we have already defined in terms of cos and v cos theta and v sin theta term, and the corresponding m you can say that are the set of measurements v naught you can say that through v n minus 1. So, we have n number of you can say measurements for this purpose. Now, then you can say that we apply the corresponding least square you can say that technique which we have learned, x equals to the pseudo inverse of a into m. Here we have considered x 1 equals to v cos theta, x 2 equals to v sin theta. So, therefore, you can say that the x can be obtained from this A matrix pseudo inverse of A and the n, m nothing but v 1 v naught through v n minus 1. So, the v can be computed from this x 1 and x 2, and that becomes x 1 square plus x 2 square. So, this gives us the peak, and then you can say that you can find the RMS value from this peak, and theta you can say that tan inverse x 2 by x 1, x 2 by x 1 will be tan theta you can say that from that x 2 by x 1 you can find out the corresponding theta value. So, therefore, from there you can say that you can find out these phasors to be VRMS with an angle of theta for the corresponding sinusoidal signal. So, this is what you can say that how you can model the corresponding sinusoidal signal for the power system relaying applications with in the least square estimation sense. Now, in these formulations we saw that there are two unknowns x 1 and x 2. So, we need at least two measurements, two samples of V 1 and V 2 to obtain the phasors, obvious, or if more measurements are available, then also you can fit into the corresponding least square sense. Say if you have, you can say there are more measurements like 1 cycle of data for the 50 hertz system with same you can say that 400 hertz sampling, where number of measurements that m becomes you can say that will be having a 8 number of you can say that samples. Then size of x becomes 2 cross 1, size of A becomes 8 cross 2, and then the size of m becomes 8 cross 1. We have 8 samples for the 1 cycle. So, 8 measurements are available. Then the Ax you can say that Ax equals to m, that becomes valid as we test. Now, let us you can say that we will go to consider some examples how we can compute the corresponding phasors using the least square estimation technique. So, as usual you can say that in our earlier discussion also on phasor estimation using DFT, cosine filter and so. So, we consider a signal V t equals to 109.53 sin 100 pi t plus 22.25 degree volt. So, samples are taken at you can say that 0.4 kilohertz, and so therefore, the delta t becomes equals to 0.9 0.025 second. We got the corresponding voltage samples which we have already seen, and this is the corresponding time index for this one with an interval of delta t of 0.0025 second. So, this leads to, you can say that data sets available now, and how we will apply the data set for the Phasor estimation technique, that we will learn. Now, let us, you can say that, as I already pointed out, we have two unknowns in this case, v cos theta and v sin theta, which we have already formulated. So, let us consider first, for simplicity, two samples minimum we require. So, these two samples are T naught and T 1. So, that corresponds to 0.1 second at the next sample. So, 41.47 and 101.01 are the sample values V naught and V 1. So, that is why I can say that we have the measurements V naught and V 1, and then x are V cos theta and V sin theta, and we know this omega, this is 2 pi f, we have considered for the Phasor estimation 50 Hz system, this is 100 pi. So, therefore, you can say you can find the corresponding A matrix. So, the A matrix nothing but sin omega T naught, cos omega T naught and sin omega T 1, cos omega T 1. So, that becomes equals to, you can say that if you substitute the corresponding T naught equals to T 0, see here, because this is, you can say that T naught, you can say that which corresponds to here is the hour, you can say that reference time for the computation of the least square chance. This time index, you can say that, is recorded by the device also. So, for our window where you can say that we are going for the computations, then in that one to see make the corresponding calculation easy, simple. So, we consider T 0 to be 0 here and T 1 to be T 1 here. So, the first sample corresponds to the 0th time and the second sample with up to the delta t. So, that least we can say that you substitute these values, you can say that here, then we got the A matrix to be 0 1, 1 by root 2, 1 by root 2, and we can say that substitute the, you can say that in the least square estimation algorithm, the technique, you can say that x equals to pseudo inverse of A and into m, then we will find the corresponding solution. So, A transpose A, you can say that becomes this, and then you can say that A transpose A inverse becomes this for the what we have computed, and then the pseudo inverse becomes, you can say that, minus 1 this. Note that because this is a square matrix, so the pseudo inverse is nothing but the inverse of A also. So, we will get, you can say that if we try, this inverse of A matrix becomes also same in this case, okay? But this is you are making a practice how to have the, you can say, the pseudo inverse computation. So, the x becomes equals to here, that if you multiply this one, then the x becomes equals to here, the first element x 1 101.37 and the second element x 2 41.47. Then, as per the already we have formulated, the v becomes, a peak value becomes x 1 square plus x 2 square, that becomes 109.53 after substituting, and the corresponding RMS value becomes divided by root 2, that becomes 77.45. So, theta is tan inverse x 2 by x 1 becomes 22.25. Estimated Phasor is, you can say that, 77.45 with an angle of 22.25 degree. If you remember, in DFT also we got the same thing, and here also the example we are talking about that peak value divided by root 2, we are getting correct value of the this part, you can say that, in this case. So, that is why I can say that we say that the corresponding Phasors being estimated is by the, you can say, the least square chance, even with the two sample becomes also pretty good. Now, we will see how by shifting the window how the corresponding algorithm works, we will see. Now, what happens that we will leave this one. So, we have a fresh sample now. So, this you can say that is now the corresponding the two samples constitute the window now. So, in this window again for simplistic we will take the corresponding for the our least square perspective, we consider that this as T 0 and this as T 1, and T 0 again you can say that we are talking about 0 second and T 1 again 0.0025. This reduces the computation burden for the system also, that is the advantage you can exploit. Now, in the M matrix, therefore, the corresponding two samples are 101.01 and 101.37. The corresponding x again remains to be same, v cos theta and v sin theta as per the formulation, and therefore, the corresponding A matrix now becomes equal to sin omega t naught cos omega t naught and sin omega t 1 cos omega t 1, same as what we see in the earlier example also. So, what we are doing here also, that is advantageous, that the A matrix we are not changing, that will lead to us, you can say that, a benefit of not computing the A matrix repeatedly and all these things. Not only A matrix, if the A matrix remains to be same in this process, even if we shift the corresponding window of the measurements, then the corresponding pseudo inverse computation this become also fixed one. So, the advantage you can say by doing the consider this approach is that A matrix can be computed a priori, and then you can say that so also the left pseudo inverse can be also computed a priori, and you fix it. and then you can say that we only apply, you can say that the corresponding m measurements whatever window we have right now, and then with that measurement you can say that if you apply you can say that multiply this fixed matrix here, then you can get the corresponding unknown vector x. Now, with this second window we will see, consider that how the corresponding x consider be obtained. So, similarly, you can say that we got the corresponding A transpose A, same you can say that what we say here, and the A matrix you can say that this pseudo inverse matrix becomes this, which happens to be A inverse also, and then you can say that multiply the corresponding pseudo inverse matrix to consider to this m, and then get the x. So, the x becomes equals to 42.36 and 101.01, and then you can say that from this x 1 and x 2 we got the v to be 109.53 and the RMS value 77.45, same what we got earlier also, and then the theta becomes equal to tan inverse x 2 by x 1 67.25. The Phasor becomes 77.45 with angle of 67.25 degree. So, what we see here that there are two windows we have observed now. In first window we got the Phasor to be 77.45 with angle 22.45, in the second window we got the Phasor to be 77.45 same magnitude with the angle 67.25, a shift in angle of positive value of 45 degree. Same thing we observe in the discrete Fourier transform also, with the shift in you can say that the window with more and more observations, the window is being shifted, you can say that with the window progresses, you can say that forward, and then you can say that. Now, what we say here that because this is you can say that the corresponding sampling rate is 4 kilohertz, and then you can say that we have 50 hertz signal. So, the number of n becomes equals to 8, and then you can say that we are getting the corresponding 45 degree shifting by this one, which is correct also, that we have discussed in the DFT, you can say that Phasor DFT based Phasor estimation also in details. Now, let us you can say that there is a chance that the signal may not be exactly fundamental, and this may be contaminated by different harmonics component, we call it a noises, because we are modeling in this in the least square sense only for the fundamental part. So, we are not modeling any harmonics, and so we can consider them as noise. So, this is a signal which we have earlier also discussed. You can say that with the fundamental we added, you can say that now the different components, the second harmonic, the corresponding other harmonics component, third and fifth, and so. So, by considering the, you consider the corresponding signal becomes distorted like this, no more pure fundamental, and then you consider the corresponding signal available, samples available are like this. With the same you can say sampling rate and this, and with one cycle becomes n equals to 8. Now, we will see consider how this at these situations how the least square estimation technique will be good at. So, again two samples, first two samples distorted signal, again T naught and T 1. So, we progress like this m and x. So, m becomes this, only m is changing, x becomes same, and our a becomes same what we have considered earlier also, and then we apply this one and we calculate, you can say that this way you can say that only you can say that our m matrix is changed. So, when you x you can say that with this m matrix same you can say that a, then that becomes equals to you are getting a the corresponding x to be this, and when we use the x we get the corresponding v to be 105.6 and the RMS value becomes now a different one 74.67, and the angle theta not 22 point something, it is now 30.7. So, therefore, you see that the estimated Phasor becomes 74.67 30.7 for the same you can say that fundamental component for the first example also. Now, the correct Phasor you can say we got earlier was 77.45 with 22, now we are getting you can say that a Phasor estimated by this process to be different. It means that only using two samples by the least square method we are not able to get the correct Phasors as expected. So, then what to do? Now, we will see you can say that what you can do also, we can have you can say that more measurements, that is the flexibility in this least square approach. So, let us you can say that I am for simplicity you can take more than 2, 3, 4, 5, 6, 7 and then do. Let us you can say that we are taking one cycle here like we did in for one DFT. So, T naught through can say that T 7 we have 8 samples here one cycle, and these are the considered corresponding measurements, you can say that these 8 measurements will be considered here. So, our measurement m here you can say that are these 8 measurements here. So, x you can say that again happens to be the same two unknowns a and b, and omega you can say that as usual. T naught you can say that we start from 0 to t you can say that 0.175, that is the 8th sample we are talking about. And for the A matrix we defined as you can say that having earlier, because now we have you can say that 8 points measurement. sin omega t naught cos omega t naught, and like this you can say that sin omega t 7 to cos omega t 7. So, I have you can say that then the corresponding substituting the t naught to be you can say that 0 and t 7 to be 0.175 and omega to be this, then we got the A matrix to be this. So, we see you can say that now that if we apply this corresponding thing to you can say that 8 measurements for this estimation of the phasors, then we get the corresponding A, the pseudo inverse matrix to be considered like this, and the x be considered if you see that pseudo inverse into m, that becomes 101.37, 41.47, and then the corresponding V to be like this, and V RMS to be 77.45, which is the correct one, and the theta to be 22.25, and the estimated phasor is 77.45, 22.25 for this first window. So, that is considered the correct considered phasors we are getting. So, what we did here, that instead of 2 samples, we took more samples which can be easily accommodated in the formulation, and by that we consider the corresponding 8 considered measurements which we took the window. So, by increasing the window, we are getting the correct phasor estimation, even though we consider the corresponding signal is being contaminated by the different harmonics. That is the beauty of the least square considered estimation technique, what we see from this example. Now, we will go something more beyond this. In many applications, what happened that the relay may require you can say that second harmonic component, third harmonic component, fifth harmonic component like this. Like in one example, in inverse current detection in transformer, for that you can say that we require second harmonic component estimation. So, different harmonic components may be required to be estimated correctly. Now, in the DFT approach and other approaches, now in the least square sense also what we have formulated till now, simple, only our target was to how to get the corresponding phasor value, fundamental component. We do not bother about other you can say harmonic components, they were being completely rejected in DFT one cycle and so. So, if you need the corresponding particular harmonic component to be estimated properly for utility you can say that in the relaying perspective and so, then what to do. Now, see here you can say that how we can do you can say that in the formulation in the least square perspective. So, what we say that we need again second harmonic components to be estimated here, let us say in addition to the fundamental. So, we will formulate the corresponding signals V and whatever you can say that the fault signal will be received by the relay in terms of 2 components, fundamental and the second harmonic component. So, these are V 1 and theta 1 and V 2 and theta 2 are the 4 unknowns for the corresponding fundamental and the second harmonic component. So, we will expand the corresponding signal model to be like this as we have done. So, this for the fundamental component first 2 terms and the second harmonic component 2 terms for the second harmonic component. Then the A matrix becomes for this case become sin omega t naught, cos omega t naught, sin 2 omega t naught, cos 2 omega t naught, because we have 4 you can say that now terms here. So, therefore, the corresponding unknowns becomes 4. So, therefore, this become you can say that the corresponding 4 cross something will be coming for the A matrix. So, these results you can say that in terms of that you have n number of measurements you can say that, then you can put the corresponding matrix to be in terms of this. So, the x becomes equals to the 4 unknowns V 1 cos theta 1 and V 1 sin theta 1 for the fundamental and V 2 cos theta 2 and V t sin theta for the this. So, we have 4 unknowns x 1, x 2, x 3, x 4 and we have n measurements V naught to consider through V n, agree. So, you can say that this is n plus 1 measurements rather you can say that we have in this case. Now, this leads to you can say that same you can say that we will apply the corresponding least square sense and then we will find out you can say that fundamental V x 1 plus x 2 square, because these are related to you can say that fundamental, and to find out you can say V 2 you can find out x 3 square plus x 4 square, they are this, and the theta 1 you can say that from the fundamental value tan inverse x 2 by x 1, and for theta 2 you can find out tan inverse x 4 by x 3, and the RMS value you can say that can be obtained by from V 1 by root 2 or V 2 by root 2 or so. Agree? So, this is what you can say that we say that if you like to get the corresponding second harmonic components, then you have to formulate in the least square algorithm, and then you can say that we can use the you can say that pseudo inverse perspective where the corresponding A matrix is being changed and so also the X matrix, and then you can say that you can get the second harmonic component fundamental. You can include like this you can say that other harmonic components in the system also. Now, note that you can say that we can accommodate the you can say that more and more harmonics, but that leads to you can say that a more computation you can say that process, because the A matrix size will also increase and more unknowns means you can say that more number of measurements also require for better estimation and so. Now, in also you can say that if you have included you can say that more number of you can say that components in the process, then your modeling becomes more accurate and the estimation becomes better with a more and more computational burden. That leads to situation in terms of that, and therefore, you can say that what you see here that however, if you see the you can say that in this perspective and all these things, if you only require you can say that the corresponding fundamental part here V 1 and this part you do not consider required somewhere here, even though you have model in the systems, then we see you can say that these matrix, these line you can say that the corresponding first you can say that the first you can say that two part, this part you can say that is nothing but corresponds to the fundamental part, and then you can say that this block you can say that represents for the second harmonic component, and then therefore, you can say that in the A matrix also and the corresponding A matrix, and so also the pseudo inverse matrix also, those you can say that portions are being required for the computation perspective. So, you can optimize your computation you can say that in accordance with the requirement for the particular relay application and so. So, what you see you can say that in overall that the least square estimation technique also provides accurate Phasor estimations like discrete Fourier transforms. If the signal is pure like during steady state or so, you can say that we can manage with less sample also, but the signal having impurity you can say that like in different situation and so, you can have more and more sample accommodated in the systems. We can incorporate harmonic components in the estimation process also, and you can say that to reduce the consider computation burden, A consider is fixed for the consider that particular window size, and so also consider the pseudo inverse also you can say that is being fixed. So, therefore, you can say that there is no need to consider that always compute the corresponding inverse matrix, and so that reduces the consider the computation burden in the process. So, in overall you see that you can say that least square is another attractive technique for the Phasor estimation perspective. We will consider that in the subsequent consider that lecture, we will see consider that how this technique can be more useful you can say that in different other applications also. Thank you.